if you have gold versus carbon, right, the backscatter electron from gold will be higher than that of carbon. So there will be a different contrast that you see. So the intensity you see from a gold nanoparticle on your surface will be different from your carbon tape, for example. Okay, so people building this sort of machine will take advantage of this called backscatter electron to use this amount of backscatter electron as a contrast mechanism, so that you can distinguish one from the other. You cannot still determine these peak locations except when you do energy loss. We'll talk quickly about this. So these are called backscatter electrons. So backscatter electron is very, very long. Why? Because of the electron, so they probe all the way down to a couple of microns. The reason is that the electron being bounced around, and as it bounces around, backscattering occur all the time. So some of them will come out, some will continue on, will continue playing around in your lattice. Okay? So your backscatter electron typically 1 to 2 microns, so it's quite deep. It's not really surface sensitive, not as surface sensitive as the second electron, but you can get a sense of what the element is about that you can see. Of course, if you have really, really high electron beam, the whole electron beam will go through, right? Will go through, and if you put your detector at the back here, you get TEM. Okay. So as I was talking about before, if your atoms are lining up like this, right? You have column of atoms, your lattice is lining up like this, right? When you do TEM, you will see you're looking down from the top. I'm plotting a side view here. So you are really doing column of atoms. That's what I meant by column of atoms. So when you see on the TEM, you see all this little. I have a TEM picture that I'll bring it next time to show you. So you can see this column of atom when you look down. So this is my picture like this. But what you're seeing is really a projection of all these atoms lining up to see. So don't get too excited when you do TEM. You have to know its limitation, okay? Know what it's telling you as you sample your data. Now, of course, when all these electrons hit, we've been talking about electronic excitation in this plot. Is all related to physics. Electron being exciting your atom in your lattice. When you have electron excitation, what does it mean? It means that the electron going from the ground state to some empty electron orbitals, right? You think in terms of first year chemistry. And this is an unstable situation. So you can have, in order to go back to ground state, this electron would like to come back from the upper state, upper empty orbital, down to some lower empty orbital, right? When you do that, this is called de-excitation. You're coming, so your primary electron beam excite your atom, and the atom going from excited state back to the ground state. And in doing so, it can do so by 2 ways. One is emit something called an OJ electron. We'll talk a little bit about that. And then the other way is to emit a photon. And usually this is in the range of X-ray. And so, and this is obviously material specific because now you're talking about exciting your material from one energy level, right, of the electron energy level to another one, and different material, of course, at different energy level, different electronic structure. And therefore, you would have photon emission at different position, different wavelength. And this, in fact, can be used to identify what kind of material you have. And so this is known as extended X-ray analysis, EDAX, usually given the word EDAX. And basically is X-ray emission. And because of the way the scattering works, this X-ray emission will occur as long as you have fast-moving electron continue excited material. So the pole volume of this X-ray emission is quite deep, is actually 3 to 5 micron. So it's not nano regime, it's in fact in the micro regime, but it can allow you to identify what material you have. Now, in the case of the other type of this excitation, the so-called radiation-less decay. Radiation usually, when people talk about radiation, they thought in terms of light. So if you don't have light emission, they call radiation-less decay. And if you emit an electron, even though electron technically is a radiation, they consider that as a radiation-less. So when you heard people say radiation-less decay, they mean electron or ion emission. And so OJ electron emission is very sensitive because it only can occur in the top 1 to 3 nanometers. So if you detect OJ electron, you are in fact in the nano regime because your Planck volume is so small. It has to come from the surface. Whereas you detect the other one, not so good because the other one is not as surface sensitive as OJ emission. Okay, so this sort of give you I like this plot a lot because this contain all the qualitative physics, what would happen as the electron beam hit the material. There's a question here, thanks.
When we are probing through scanning electron microscope, we have two modes like secondary electron mode and then backscattered electron mode. But how does the detector differentiate between these are secondary electrons and these are backscattered electrons?
Okay, so the question is that when we are doing electron microscopy, you have two types of electron emission. You have a secondary electron and backscattered electron. The question is, how does the machine detect it? It's very easy, actually. The way you detect it is by a different detector. So they use different detector to detect the secondary electron emission. And another thing that you can think about is that the secondary electron does not have very strong directionality. In other words, secondary electron is just like a charged cloud coming off, right? Coming off. So the angular distribution of secondary electron is very isotropic. It's much more isotropic than the backscattered electron. The backscattered electron is preferred to go in the forward direction. In other words, if you go in the forward direction, it reflects back. So you could position your detector very close to your primary beam, directly on top. This is why a lot of the secondary electron, a lot of microscope has the secondary electron directly on top of the primary beam because this is the best position to detect backscattered electron. And then in the case of secondary electron, you can detect anywhere. You can detect in the forward direction, or you can detect on the side and so forth. Okay. So and also of course in the case of detection, the secondary electron is slow-moving electron. So detection technology will be different. So what you need to do is that you essentially catch the secondary electron. You let the electron drift close to your detector, and then you have some sort of potential to accelerate your secondary electron to very, very fast, the kilo of electron volt. And this kilo of electron volt hit a scintillator, which will basically convert electron into light, and then you have some sort of a light beam, and then you can measure the current. So generally, that's what you have. So if you look at the secondary electron. Whereas in the case of backscattered electron, you can actually detect directly either directly the electron current, because they are a lot more, or you can detect in the same way using a scintillator technology to detect it. Okay. Yes.
Where does that light come from?
The question is, where does the light come from? I guess you mean the light. You mean the X-ray light?
No, the light.
Oh, the light. Yes. When they say light, so you have X-ray emission, and you also have optical emission as well, right? Because depending on how far your excitation goes, right? So when it's not a very precise language. So let me try to explain. So you have different energy level, right? So if you move an electron, right, excited electron. So let's say you feel your electron up to here, right?